Hello everybody and welcome to another day of CS 219. Today we are talking about hard drives and secondary storage. It is chapter 7. Okay, so here we go. So hope you'll do good in the test. I will go ahead and make the TA. I believe the TA posted the grade online. He can go over some of the questions of the test on Friday with you. You will have your regular discussion session on Friday. For us, for the class, we're just going to keep going because we got a lot to cover. So let's go ahead and get going then. So the chapter deals specifically with secondary storage, but it's mostly a focus on hard drives and of a special sort of way of storing information in hard drives, which we call RAID, which allows us to do one of two things. Either, well, not necessarily exclusively, but together have more space available in terms of not space, actually have we'll have more space, but at the same time not everything in one drive, which means that we want to split it between multiple drives to be able to speed up read and write, and also to have some sort of redundancy in case of a hard drive failure. So that's what we kind of go to. But before that, we kind of have to talk about in general how hard drives work. And as for your question as a practice test, it will be graded for completion, for participation points. So, yes. Okay, so drink some water. So, let's go ahead and start by defining what a magnetic disk is. And for that, I'm going to go ahead and turn it over to the PowerPoint. So this is a PowerPoint from the book, right? Here's the cover for that. Okay, so technically, we all know that the more space you have, the cheaper memory is, but the slower it is, right? And so it's impossible to store everything in main memory because main memory is volatile, and when you turn it off, you lose the information, so you want it to kind of remain afterwards. So we need some sort of external or secondary storage to be able to store data in a non-volatile manner. And also because even if main memory was non-volatile, it would be very expensive to store all the information there, right? And so because of that, the most popular, at least nowadays, way of storing information is going to be in a secondary disk, which is usually a hard drive. Now, solid-state drives have made a long way, especially in places like where people can afford like nice computers. But still, I'd say in the regular, the average household, there's probably more hard drives still than solid-state drives. But we'll talk about that. So, what is a hard drive? A hard drive is basically a platter. It's a little disk. In fact, I might actually here. I can go get one so I can tell you what it looks like. Okay. All right, I'm back. So I actually got one of these as well. So this here is a hard drive. Yeah, this one is a hard drive. This is actually a really old hard drive. This is not what they look like anymore, but it's better than nothing. Oh, hold on a second. Let me fix that. Fail. Okay. That's very annoying. But, okay. So, this is a hard drive. Or at least this is the casing of a hard drive. The hard drive is actually technically inside, okay? And so there are different shapes and colors, actually, mostly just shapes of hard drives. And this is actually what the old school hard drives look like. Now they're a lot thinner. I don't have one easily accessible here. They're somewhere in storage, but this will do. So basically, you see there's some sort of chip. Well, because it's green. The green screen is messing it up, but it's green. And there's a little chip there, or not chip, sorry, here. Well, you guys tell me, what is this called? What is the green thing here called that holds all the connections together? It is called a, let's see if you guys remember, PCB, which stands for logic board, printed circuit board. There you go. So yeah, it's a printed circuit board. So somebody comes up with a design for this, and then they say, bam, stamp it and print it, and then you can hook up all your little chips and things like that to it. And so what is in here, you know, and since this is really old, I could have actually probably taken this apart to show you, is in this case it's actually a 3.5 inch. It doesn't even say, but this is probably like 4 gigabytes, maybe 8 gigabytes, maybe even less than that. And so what it turns out is a circular platter, and those are usually made of substrate, which is an aluminum or aluminum alloy, as the thing says there, but more recently glass. And by glass, I think, at least the way that I understood it, was more like porcelain, and sort of a porcelain platter. That's kind of what, if you would imagine it as. And it's a disc. It's actually a spinning disc. And so those are usually encased in something where you hook it up to the computer, and they have connections that go directly to the motherboard. Those connections can be what is known as IDE in the old days, which is what this is, I think. This is what an IDE connection would look like. And then nowadays, well, not even nowadays, because nowadays they're kind of phasing out. But in the regular days, I suppose, it was a SATA connection. But now they're moving into PCI Express, like NVMe, and so on, and that kind of thing. So, yeah. Okay. And so let's talk about how that is actually done. Okay. So the way that you store information in a hard drive is you have this little platter that is spinning around, and maybe I'll switch to the, well, there's a picture here, but I feel like it might be better to draw it. And so you have a disk. And that disk, you know, if we go ahead and sort of flatten it, it has a lot of tracks in it, okay? And the track is kind of like a little circle within the circle, okay? So if we flatten one of those tracks out, you know, make it look like a line, it turns out that on top of this track, we're going to go ahead and put a lot of little tiny mini magnets, which is more of magnetic material, which are basically one next to each other, like that. There's a little space in between. And what you end up doing is you have some sort of stick, basically, which you can call like a little needle or something. And on top of that stick, we're going to have a coil that you can pass electric current through. And what happens is, one of the properties of electricity and magnetism is that if you pass electricity to some wires, it generates a magnetic field, which can magnetize anything that is near it. Obviously, the higher the amount of electricity going through, the higher the magnetic field. And the reason why a magnetic field happens is kind of beyond the scope of this course. But the way that I understand it is, the electrons moving through generate, you know, they generate a resistance as they go through. You can think of that like there's friction involved, and that friction generates energy, and that energy is in the form of a magnetism. I think that's kind of how it works, but again, I'm not a physicist, so you have to ask those guys for that. Okay? And so basically, what we do is, you know, each of these little magnetized materials, you know, there can be sort of two states to them. One of them is where they're magnetized, and you know, maybe they by magnetizing them, you can think of it two ways. You can think of them as sort of like sticking up, or you can also think of them as having sort of being polarized, you know, so they have a direction. So like they get magnetized in this direction or that direction. Either way, we have two states, right? And if we think back about what we talked about when we talk about memory cells, is that the way that we can have memory is it has multiple states, and we can detect each of those states, and then we just assign a 0 to one of those states and the 1 to the other one. So similarly here, what we end up doing is we magnetize the little squares here, and that becomes a 0 or a 1, depending on, say, if you think of it like which direction it's pointing to, or if you think of it like a little hair that's just down, and then when it's magnetized, it kind of straightens up, okay? And that's basically how we store information in a hard drive. We have a lot of these little tiny little squares, and each of those is a bit, and then we just magnetize them in a specific order, which is going to represent the binary equivalent of that. That's kind of in the most basic level, okay? So let's go back to the PowerPoint now. And so the reason why this is made up of a glass substrate or a aluminum alloy and things like that is because what you need to do is the base of the actual plate has to be of a non-magnetic material, because we don't want the base to interfere when we magnetize this, right? So if you think of the little squares, you know, they have to be lying on something. But if that something is magnetic, it can mess with the way that we're magnetizing things. So we want to make sure that's not magnetic. Then we have the magnetic layer that we actually can magnetize or demagnetize, right? And so the benefits of using a glass substrate over the aluminum one is that it's, I believe it's, well, it says here, it can be thinner, so it can support, when we talk about how it reads, it's going to be able to be sort of a smaller drive and a closer distance from the read head. It's also more resistant to shocks and movement. Back in the day, the old hard drives, you had to park them. So if you wanted to move a computer to a different place, you couldn't just move it. You could actually damage the hard drive, because that little needle, if you think about it, it's so close to the hard drive that the vibrations can actually make you scratch the disk. And think about it this way. This hard drive is spinning very, very fast. We're talking about spinning potentially 5,000 revolutions per second or 7,000 revolutions per second approximately, okay? That's the RPM when you look at a hard drive. That's the two main numbers they sell nowadays is, I think, 7,200 RPM and then 5,600 RPM, I think. I don't know what the other one is. Let's see what this one says for the RPM. If it even says that. Nope, I don't think it says that. Nowadays, most hard drives have a little stamp here that has all the details. This is so old that it doesn't say it, but it is made in Japan, so that's like, ooh, it's pretty fancy. It even has a way to set up jumper circuits for different things. But oh, here we go. So this actually does have that parking ability. There's no way I'm going to be able to show this in the webcam. But down here, it actually has a little thing that says you set a specific configuration to park the disk. But this could also be done with a command within the MS-DOS and things like that. And what it would do is it would move the needle sort of locked up, and it would lock the drive so it wouldn't shake, so it wouldn't cause damage to it. And so that was the problem back in the day. And as we'll talk about here in a second, we kind of improved that. And one of the big ways that we improved to avoid having that problem, you know, because otherwise we could have laptops that are actually using a hard drive, would be to change the way that the substrate is, okay? And so again, just to make sure we understand the definitions, the substrate is going to be the magnetized part. So those are the little squares per se. And then the circular platter is just where it's lying. And I think, from my experience, from what I heard, is that the actual platter itself is like a porcelain platter or something. And that's because porcelain is non-magnetic as far as I know. And so you can't make the platter out of metal, because it can get magnetized as well and mess things up. We don't want, once we magnetize something set it as a 1, we don't want it to accidentally get changed to a 0 because of the surrounding magnetic fields messing with it. That also poses a problem, because if we look at what I drew here, you know, each of these, you know, suppose that this one is magnetized and represents a 1, and this one is not magnetized and represents a 0, and then they say this one is magnetized and represents a 1. These are magnetic fields of their own, right? And so, in fact, when this thing is reading, you know, it can use the same needle or a different needle depending on the systems, but it's actually going to detect the magnetic field, and that's how it's going to be able to read the information. And so it needs to be able to read that, but then when it moves to this one, it has to be able to make sure that there's no magnetic field, and then here's this magnetic field. We don't want the surrounding magnetic fields from this one and this one to interfere with the 0 and make it think that there's a 1 here, right? So they have to be separated enough. Furthermore, we don't want the magnetic field from these to kind of physically change this to be a 1 as well by magnetizing it. So they have to be weak enough field that they don't magnetize the surrounding bits, but strong enough to be able to be read by the reading head, which is quite an engineering challenge if we think about it. So switching back to this. So here they have on the book a little bit of a better drawing than what I have of how this kind of is set up. And so this part here is going to be your head, okay? And the head and again, is to some sort of stick that's holding it. And then these are the different magnetized material that records the information, which they call recording medium. But basically, it's the material that can be magnetized. And as you can see, it kind of has in this case, north and south pole, depending on which direction it's magnetized towards, it's depending if it's a 0 or a 1. And ignore for now these two things, because what they did in the picture is they put two different reading methods. So ignore this one and this one. Just stick to this one. So as you can see here we got wires that can pass current. And then basically what happens is you go ahead and you magnetize this, which will then magnetize this to write, and to read, you also detect the current. And by detecting the current, it actually generates electricity. If you pass a coil by a magnetized material, it generates a little bit of electricity. And so we can detect that electricity being generated, and that's how we can read from the hard drive as well. So now, if you're asking what these are, is there's a certain limitation to being able to do this whole reading and writing thing, because that involves being able to detect the magnetic field. But later on, the book talks about what the MR sensor is as a way of improving this technology by because right now we're using the same head to read and write. But once you have a partially shielded magnetoresistive sensor, which is what MR stands for, that has an electrical resistance, and that's what it uses to be able to detect how this is magnetized. By passing a current through the MR sensor, resistance changes are detected as voltage signals. So that's how the MR sensor works, which is it's a better technology because it allows, as this book, the MR design allows higher frequency operations, which at greater storage densities. So here's the thing. We want to be able to store a lot of information in the hard drives, and as you can see historically, hard drives have increased in size. Back in the day, something like this, 1 gigabyte was a big deal. The smallest hard drive that I can remember having is a 512 megabyte hard drive. Okay, and that was when I was really, really young, and I was using actually a computer back then. But nowadays, I have a terabyte hard drive. I have a 4 terabyte SSD. We have grown pretty fast in terms of space. However, the size of hard drives, so the biggest hard drive that I have is, I have an external hard drive, but internally I have a 1 terabyte hard drive, I think. That's the biggest one that I have. So, however, it's smaller than this. And so how can we fit more information while keeping the same amount of space? And it's quite simple and quite hard at the same time. All you do is you make those little squares smaller. You basically, each of these lines that you have in this hard drive are called tracks, and so you put more tracks by making things smaller. The problem with making the little squares smaller is that you need a needle that is more accurate to be able to pinpoint to the right location, and to be able to not have enough electrical current that generates such a big magnetic field that changes neighboring bits. Because if it's smaller, if you think about it, okay, if for example, the book makes mention of a floppy hard drive, okay? Sorry, not hard drive, just a floppy disk. A floppy disk works just like a hard drive. It's a magnetic sort of disk, which has its own little. Actually, I don't think the floppies themselves have the reading head, but that's actually on the drive itself. But still, it works on the same concept of having a magnetic. A read and write head and having the magnetic disk. However, the density of a floppy is very, very low. You basically can keep around 1 megabyte of information in the floppy, and it's about the same size as a regular hard drive is nowadays. That's because all of these squares are so big and separate from each other that it doesn't need to have such an accurate read head. But the moment you go more accurate, more smaller, it needs to be more accurate to be able to line up to the right location, or the right little square to be able to read the right amount of data. Okay? And so here you can see that the name they call it in the book is the head, so the reading head, or conductive coil. And as I said, some systems have a read and write, but originally there was just one head for both read and write. When you have a read and write, that's when you have the MR sensor for the read, and then the other one for the write. As you can see here, the right mechanism exploits the fact that electricity flow into a coil produces a magnetic field, which is what I said. And the right head itself is made up of easily magnetizable material in the shape of a donut. Yep. This is all from the book. So I think that's all I can want to say about that. So from now on, let's actually move about how the hard drive itself is distributed. So, okay, I hope you guys have at least seen like a record player, right? You know, you put this. It's got a little needle, and you put it in, and then it starts spinning, and then as you're spinning, it plays music, right? And so in that case, the way that it works is depending, you know, the disc is not flat. There it has little ups and, I guess, throws and hills, you know, ups and downs. And then based on that movement, it has to do with the pitch of the music, right? And so in the hard drive, there is no up and down motion, but you're still reading in the same concept of something spinning. So that's kind of where they took the idea to create a hard drive. This isn't something that people just invented with hard drives. It's an old system that was used in music disc players. You know, I'm starting to question if you guys know what those are. So let me pull up a picture of one. What would they be properly called in English? Well, here. Well, that's not the best drawing of one. This one. Yeah, this one works. So that's what I'm talking about, okay? And in this case, it was just a plastic. Not plastic. It was a... What is this made of? It's like a clay material. Paste. It's a paste. It's a plaster, I think. It's plaster, I think. And so in this case, the ups and downs of this is what generated the music. So this is kind of the inspiration of a hard drive. If the surface of the disk is not magnetized, how are magnetic patterns recorded onto it? Because it's a two-layer thing. Basically, you have the surface that's non-magnetized, and then you have the magnetized surface. So what I'm saying is, if we look at it sideways, if we look at the disk sideways, you know, here's a disk, you know, there's a hole somewhere so it can spin. And so this is just some material that's not magnetized, okay? So like think of it like a ceramic. So no matter how much magnetic fields you make this go through, it will not get magnetized. Now, most materials, if you feed enough magnetic current, eventually they will magnetize, but some are easier to magnetize than others. So plastic, for example, is very hard, I suppose, to magnetize if anything. So anyways, what you do is on top of that, you put a layer of magnetic material. And it's not just a smooth layer, you actually kind of leave spaces in between. So that's what I'm saying when I'm saying you leave little squares. And the reason you want to leave some space, obviously this is not to scale, is so that you can separate each of the bits, right? There needs to be a space in between them. Okay, so hopefully that answers your question. So, how do we organize things within the disk? There are two sort of main ways. One of them is going to be how CD-ROOMs are, which is kind of like how the old school music players are, which is sort of a put the needle in the center and then it slowly spirals out to the end. So that's how it kind of reads information. But hard drives are not actually like that. Hard drives have independent tracks. So they're sort of like disk within disks. And as you can see here, an example of that, you can see how, look at how S1, the labels here are iffy, but this is one track right here that's on white. And then the light green is another track here. Even though this one's a different color, just ignore that part. And finally, this outer layer is another track. And in between the tracks, you can see this gray material. The gray material is non-magnetized material, and that's sort of a buffer to separate, not a buffer in the computer science term of like buffers in memory, but in the sense of like it's just a space that's empty between different tracks. And again, that's done because we don't want to accidentally, if we have two things together that are supposed to be magnetized differently, they're going to start messing with each other, and that's going to cause problems. So we need to separate them, right? So not only do we have to separate things sort of next to each other and sort of before on the head, but also on the sides. So if you can think of this, even though this is a sector, think of it as just a byte, okay? Or even a bit, actually, just a bit. So if this is a bit, you know, you need to separate it from another one by having an empty space here, but also if there's another bit here, you also need a space in between here. So all around, there has to be spaces, okay? Think of it like a block in a house, you know, in a city. Like a city block has roads on all four sides, and then there's another city block, see? And there's roads on all four sides. They all have to be buffered out. They can't be touching each other on all four sides, okay? Now, in a practical standpoint of view, even though things are separated from individual bits, the way we're looking at this picture is more of in sectors. So the information is kept in sectors, which is just a block of information. And so each of the little spins here, or the circles here, is a track. That's what it's called. And each of the tracks has sectors in it. And so that's what they're trying to do here. They're saying sector 1, sector 2, sector 3, sector 4. And then the second track has a sector as well, and so on. So like, if there's 18 tracks on the hard drive, which means there's 18 circles. I think the word is concentric. That word rings a bell. I think it was in the book somewhere. But I don't remember what concentric actually means. Let's share the same center. Yes, yeah. So it is a concentric circle. So they're all concentric circles, so they all share the same center, but there are different sizes. And so they all have the same, in this specific case, they all have the same number of tracks. And so what is something interesting that happens here? If they all have the same number of tracks, you know, in this case, they have, let's say this is going from 1 to 6 right here, okay? I know there's stuff here, but just ignore that. They all go from 1 to 6, but notice that this space is much smaller than this space, right? And that's just because of the way that a circle works. The further out they go, there's more space within the same degrees of difference, right? So like if this is degree 0 and this is degree 30, you know, and then this is a radius of 1, you know, centimeter or whatever, then this amount of space is going to be smaller than a radius of 0 and a degree of 0 here, a degree of 30 here, but a radius of from like 1 to 2. Even though that's also 1 centimeter here of width, it's going to be bigger because you're outer in the circle, right? And so that's going to cause us some issues that we'll come back and talk about. But that's sort of the most basic way of organizing the hard drive. And so ignore this bottom picture. We'll come back to it when we talk about like dual layers and things like that. But here's a better example of how things are split out in the different tracks. So the first 2 lines here, you can think of that as a track, okay? Actually, they're 2 separate tracks. And then you have a buffer zone. And then you have another track. Then you have buffer zones, and then you have another set of tracks here, okay? Now in this one, things aren't exactly lined up, as you can see. Here inside we have 1, 2, 3, 4, 5, 6, 7, 8, 9 tracks, and outside we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Pretty much a lot more tracks, right? So those are 2 completely different ways of having the information stored. So let's talk about why they're different. So here's a little problem that happens in the book, talks about it. So when you're reading information, right? So what happens in this hard drive, and I haven't really mentioned it, is this thing is spinning really fast. Because there's 2 ways to do it. So if we have the information here, and we have the reading needle, which is this, and then here's our actual reading head, you know, and so this thing, if I want to read from this information, one of the ways that I could do it is I could just have this not be spinning and then have this thing move back and forth, right? Looking in the disk where it needs the information, like this. However, that's a very complicated process to do. It's too much engineering involved there. The other way that we can do things easier is we can just make this spin nonstop, okay? At a constant velocity. And so now that it's running at a constant velocity, the only motion that I really need to do in this system is to move this in and out from the center. Just like that, just one axis of movement, just in and out. If I want to read the tracks in the inside, so here, let me draw 2 tracks for you. So here's 1 track right here from there. Well, assume it's in the same center. And there, so there's 1 track. And then the other track is going to be more outside here. Again, assume that it's actually centered and concentric. Okay, so those are my little tracks. There's a track there, and there's a track there. Okay, and so if I'm trying to read from the inner track, you know, I just move this thing there, and now the disk is spinning, so I can just stay there. And because this is spinning, I'll get all the information on that track. If I want to read the other track, I just move back here, and because the disk is spinning, I just find the stuff. Now, suppose that I only want to read like this piece of information here, and maybe this piece of information here, and maybe this piece of information here. What I do is I take the head and I move it to the inner track, and then I wait for the disc to spin because it's spinning, right? And right now, you know, in this case, okay, I'm right on top of something, so I can go ahead and read it. Okay, so I read that. But if I want to read the one that's over here, this one, I have to wait for the disc to spin and for the actual sector to fly over, or sorry, not to spin under the reading head to be able to catch that information. So I gotta wait for this whole thing to spin. So, you know, let's go ahead and spin it, I suppose. So it's spinning, and then bam, finally it gets there. And so from there, now my reading head was standing here this whole time. It actually was able to read that. Then it's got to move back out here and then wait for this thing to spin there. So yet again, it would basically just, you know, be spinning around, not changing sizes like I did there, morphing into different sizes. But eventually it goes there. And, you know, this thing is standing here and is actually able to read it, okay? So, yes, this is next generation of visuals here. But, yeah. Okay? And so, here's the thing. If all of the tracks are the same, if we have the same number of sectors within the track, so let's call this track, I don't know, maybe it's like track 3, and this is like track 11, just because of the number of layers. One of the ways we can do it is we can have each of them have, you know, 6 tracks. So if they have 6 tracks, it means we kind of just, actually let's do 8. It's an easier way to split things up. If they have 8 tracks, you know, sorry, if they have 8 sectors per track, then this itself is a sector, and this itself is a sector, right? But here's the thing. Do you keep the same number of bits on each of them? Because here's the thing. Suppose that here in this is an OG hard drive, really old. I can only store 1 megabyte of information in this track. If I can't go smaller because then I haven't reached the level in technology that I can make things that small. If I make them smaller, the magnetism gets messed up, okay? So here's the thing. Outside here, you know, technically there's almost twice the size as the one inside. So I should be able to keep 2 megabytes of data, right? But here's the thing. In the easiest system, I want this to also be able to store 1 megabyte of data so that I can keep things consistent. Because here's the issue. If I want this to store 2 megabytes of data like this, then my addressing system can become rather complicated to know how much of the spin has to do. Because like if I know that there's data over here, you know, I have to spin it half the way there. And then think about it this way. Let's say that each of these sectors takes 1 second to read, right? If the innermost thing here can, you know, contain 1 megabyte of data, you know, I can't make this contain more because it would mess things up. However, out here, I can make it contain more. And so what I'm trying to say here is the problem arises because it's not consistently the same density of data. And if you keep the same density of data, then it's a lot harder to kind of address the information, because this stuff, you know, and the book has an equation about this. If you compute what they call the rotational, I think it's called the rotational or angular velocity. Let's see if I can find it out. It's called, on the book. It is called the constant angular velocity. Okay, so let me write that down. Constant angular. This becomes like a trigonometry problem, basically. Okay. So constant angular velocity, I guess abbreviated as CAV because that's what it stands for. And so basically, you know, if what it means is the information, if it's able to be scanned at the same rate by rotating the disk at a fixed speed, it's known as a constant angular velocity, okay? And so one of the sort of basic things, I guess, with spinning things is that when you have a disk spinning, the inside of the disk spins slower than the outside of the disk, right? So if I'm spinning this at like 6 revolutions per minute, or per second, I guess, that's a little faster, you know, and let's say that the disk is, I'm trying to make this easy, 2 centimeters wide, okay? If the disk is 2 centimeters wide, you know, that means a radius of 1 here, and this thing is running at 6 revolutions per second, how fast is the outside of this going compared to something like in the middle of the disk? And it turns out that the outside is going much faster than the inside. Even though, you know, if it's going 6 revolutions per second, you know, in 1 second, it's going to have rotated, 6 times. So in 1/6 of a second, it's going to be rotated 1 time. So if we say in 1/12 of a second, it's going to have rotated 1/2 of the spin. So something here will be here, right? The distance here, how can we calculate that? Well, if we think of our area of a circle, you know, the circumference of the circle is pi times d, right? So if we want to compute half of that, it's just pi times d divided by 2. And so in this case, the d of the inner track, let's say that this is actually 1 centimeter, because the whole thing is 2 centimeters, right? So the inner track, we'll say it's 1 centimeter. But the outside track, which is the full width of the disk, is going to be 2 centimeters. And so if we want to compute the distance that is going to traverse in half of the spin, you know, we can basically say that it's going to be pi times d divided by 2, in which case it's going to be pi times 1 divided by 2 for the inner track, and then the outer track is going to be pi times 2 divided by 2. And so let's just, to make math easy, let's just say pi is equal to 3. So 3 times 1 divided by 2, 3 times 2 divided by 2. So this becomes 3/2, which is 1.5, and then the other one becomes 6 divided by 2, which is 3. So basically, and this is a property that it's not magic that we got twice the size. As you can see, it's just, you know, the higher the diameter goes, the higher this thing goes. But as you can see, it in the same amount of time, the inner track ran half the distance that the outer track did, which means that the outer track is going twice as fast as the inner track. Okay, and if it's going twice as fast, that can pose a problem if we can't read that quickly, right? If our ability to basically detect magnetic fields and pass them in is limited to basically being able to read, I don't know, 5 bits per second or something, you know, these are just random numbers. And in the outer track, in this amount of 3 centimeters, there's 10 bits, then we're going to miss some bits, right? So this creates a problem in how we can separate the data to be able to kind of read it with the different speed changes, okay? So, yeah, so that's kind of what we're getting into here. So one of the solutions is we want to keep all the sectors the same size. Well, here's the thing. The bad solution, let's talk about the bad solution. The bad solution is as follows. If you do it the way that I have it, where you have the same number of sectors per track, you're wasting space in the outer ones here, because these outer ones, you know, if the limit is 1 megabyte of this space, and here it's 2, but you're still keeping 1 megabyte because not only is it spinning faster, but you want to space them out so that you can read them as quickly, then the solution again is just to make all of them the same size. Because if they're the same size, you know, remember, this is going to take, let's say there's 4 of these here, and there's 4 of these here, right? But you could technically feed twice the number of data out here than you could inside. And here, you know, it's going to take, how much did we say? Let's say it's going to take, it's going to be 1.5 centimeters a track, and this is 3 centimeters a track, right? But they take the same amount of time. But if you space things out here, you don't run into problems reading, because even though you're going faster, you have more space between the different blocks, so you can kind of catch them as you go, or you can even make the little magnetic squares longer, right? So you could catch them. So that doesn't cause a problem with the whole reading and writing, even though you're going faster, because you can just sort of stretch things out so you can catch them. So even though you're faster, you can still do it. The problem is that you're wasting space, because you have this low density. You're essentially wasting space where you could store more information, right? So ideally, you want to keep the tracks just as small as you can, as tight together, and not worry too much about the ability to read things. So to be able to do that, you need to have 2 advances in technology, I suppose. And the biggest one is the one that you can actually capture. Even though you're going faster, you can still capture the different bits as the little different resistances with your MR sensor. And in addition to that, you want to have logic that can know that the outer tracks are going to be going faster. So this thing actually needs to physically like speed up its scanning speed so that it can actually catch the faster running bits. So even though things are moving faster, it knows that it has to read faster. If they're going slower, then it has a little more time because it's the inner part of the disk, right? So that's kind of the technological difficulties of doing this. So the other system where all the sectors are the same is where the other picture comes from the book, which is this picture here. So again, I guess this actually shows you a good one. So constant angular velocity is this one. Again, all the sectors are the same. So doesn't matter that you're going faster on the outside. And then this one is the multiple zone recordings. But this is a lot harder to keep track of because you will have to read faster on the outside than on the inside because of the faster spin rate. Okay? So planetary orbits, I guess. Except we don't really have to compute delta V changes here. We don't need to worry about like our perigee and apogee and all those cool things. That would be a cool class to teach. But yeah. Okay, so we can probably talk about this now. Skip ahead. In the book, they eventually, it's kind of like when I was reading the book, I think I read this chapter yesterday or 2 days ago. I frankly can't remember. I did finish reading it today, the magnetic tape part. But when I was looking at this, I was confused why they had this picture here. And then they'll talk about it for like 2 pages later. So, and then they finally go back and refer to it. The reason is because I guess they wanted, it kind of makes, I mean, once it got there, it made sense. But this picture refers to the fact that you can keep multiple layers of magnetic material within the same hard drive. So what they end up doing is, just like in any other parts of the technology, you know, Moore's law and everything, you know, we have to find ways to kind of keep being able to sort of have that momentum of increasing amount of information that we can keep here. And so one of the ways, sort of the cheating out way, but still perfectly legit, is to just make things in parallel, right? And so what's better than one hard drive? 2 hard drives, right? But if it's even better if they're both in the same like hard drive, right? So that's what they end up doing in the example here. So this is what is happening here is there's multiple platters within the same sort of casing. There's multiple mini disks, like the disks are stacked on top of each other. But it's actually one big piece. But in reality, they're tiny little stacked ones. And what ends up happening is each of the platters has its own magnetic material on top, and it has its own read heads per surface. You know, there can be read and write or read or write, you know, depending if there's the same one or together or separate. And they're all basically lined up in sync as the things are spinning. So you can basically write more information at the same time and read more information and have 4 times the capacity or 3 times the capacity. Basically, how many layers you have. So that's one of the ways to kind of have more information, you know, basically in parallel. That does remind me, by the way, I never mentioned one of the words that I wanted to talk about when I was talking with memory, and that with DRAM. By the way, DDR, when you think about like DDR RAM, you know, DDR SRAM or anything, DDR stands for double data rate, I believe. And that is basically just going to be, you can transfer twice the amount of data. So basically, that you could think of this kind of like a DDR sort of same sort of mindset. Okay, so I just remember I wanted to mention that. Also, between what was the thing I want to mention last time? Well, I want to mention NOR and NAND, which I didn't, but I'll talk about that when we get to the SSD. So yes, just a little insert of information there. Okay, so that pretty much covers the beginning of this. We'll go back to the error code thing when we talk about RAID. They also talk about how much data to store per sector and things like that. So I'm not really going to go into that too much in detail. In the book, you can look at it. But essentially, you need to have a gap in between each piece of the sector. So again, to separate the magnetic material. And then this little sync thing is a little flag to the head that you're getting to this specific sector. You know, to address mark is kind of the same thing. It's kind of like to tell you where you are in the disk. And then you have the information. And then you might have some error correction code, like we saw Hamming code already, right? And there's other ones like it. So that could be useful again, if you know, because there can be read errors. And so the standard they come up with is a 4K byte sector, which is the bottom one. So yes. Okay. So this kind of summarizes that. So we have, by the way, most of your hard drives, in fact, I'd say pretty much all of them, they're always going to be spinning at a constant rate. And this is different than something, for example, like a CD drive. A CD drive, there it actually changes speeds and resolves the problem of the outer layers being faster than the inner ones. Because what happens there is it has the same density throughout the disk, but it slows down when it's reading the outside of the disk because it's going faster. So it slows down so that the read head can always be reading at a constant rate, and the disk just slows down. And if it's going on the inside, it speeds up, or basically it's going the same speed. Okay, so if you think of the center of the disk as the neutral speed, then in the center it speeds up, and then the outer side it slows down. If you think of the outside as the normal speed, then I suppose it slows down as it goes into the center. Okay, so that's why if you ever had a CD drive, you would hear it like, and then like you kind of like change different RPMs. That's because it was reading different parts of the disk, which actually brings up an interesting point. So if you think about RAM, random access memory, it's able to read anywhere at any time at a constant time, right? But if you remember, hard drives, you can't just go anywhere at a constant time because there's actually a physical manipulation that needs to happen to be able to read from something, okay? So like, let me give you the example using actually this work of art of a picture that I have here, right? So let me, I uncopied it. Let me show you something here, again, with some art. Okay, so suppose that I am reading in some very important piece of information. Maybe all of the student grades are stored here in this hard drive. And I'm trying to read all of them out because I need to fix them, right? Because remember that issue with the question in the test? One of the questions that was the answer was wrong, right? So I have to go back and fix all of them because Canvas sucks. Actually, I didn't. The TA did, but yeah, bless the TA. But anyways, he's really doing a good job, by the way. I guess we actually should give him a shout out. But yeah, anyways, basically, suppose that the information, ideally, in the best case scenario, let's just say the information is stored here, here, and here. Okay. Maybe here there's 10 students. Maybe here there's, well, I guess maybe 8, because there's about 25 of you around. So let's say there's like that much. Okay, and maybe there's a piece here. Okay. So he is indeed, yes. Thanks, Sam. Indeed. He can't see the chat here, but I guess he will because I have the chat logs. But yeah, and so maybe here there's like 2 students. Okay, and so here's the thing. If I have my read head here, so this is my read head, and I kind of actually want to put it outside so I can move it in. Yeah. So maybe actually I'll put the read head here. And so if it's here, this is perfect because now the disk is going to spin. And again, it's really kind of really hard to show that. But as the disk is spinning, so let's say it's reading there and the disk is spinning around and it's able to just scan all that information as it spins through, reads all the information in, and then the disk is constantly spinning. And let's say now I'm ready to update the information, right? So I did whatever I had to do in CPU, back to memory, and now it's going to update the hard drive. It waits for it to come back along, and bam, it starts writing over all the information, and we're good to go. Okay? That's great. It's great and amazing because it's all kind of one after the other. But it's never always that the case. What really can end up happening is what's known as disk fragmentation. Maybe some information is stored there. Other information is stored there. Maybe other was here, other is here. And in this scenario, things are a little bit slower. Because suppose I want to be able to read all the information that I marked in sort of that reddish orange. And I'm here. Well, if I'm here, that's really bad because now I got to wait for this whole thing to spin around. And let's say that I actually don't care about the order I read it in. But that might actually matter. Like, it might be a specific order I have to read it in. But let's say that I don't, okay? Let's say I just want to read it all, and then I'll fix it all together later on in main memory. Well, finally I get to read this piece here, then I gotta wait for it to spin here. This is just time I'm waiting for it to physically spin the disk, because the disk is spinning at a constant speed, but that speed is not infinite. It's a limited amount of speed, right? So let's say it's 7,000 RPMs. That means 7,000 revolutions per minute, which means it's gonna take physically time to actually rotate it. And so the time from here to here is actually time that we have to just kind of wait. And then it's going to read this part, and then the reading head has to kind of move here, but probably by the time it moved here, this thing was like spinning out, and then probably here. So now it's going to have to wait, then finally read this part, and then it's finally going to read the second part here, which is this, okay? So that takes time to do, okay? That actually takes time for us to move that. And the book provides us with a formula to compute the time it takes to do that, which is in the different variables it takes. Is it on the PowerPoint? Of course not. Okay, that's fine. So that's on page 217. And so we have a couple of things. We have seek time. We have rotational latency, rotational lag. And we have, or also known as just latency time, so lag. And then finally we have transfer time. And we're going to represent them. Let's see, I'm going to use the same ones as the book. So seek time, they use TS. And then lag, they're going to use TL for lag. So that one's for that one. And then for transfer time, they use TT. That. And then finally, like the sort of summarized time is known as the block or sector access time. So they spell block like that. Don't ask me why. They also just call it access time. Either block or block access time. It really does bother me how they spell block. There's probably a reason for that. But anyways, that one is just called TV. And so the formula, I don't know, it might be a typo, but I don't know. Well, if it's a typo, then we're all learning it with a typo, I guess. TS plus TL plus T. Okay? And so let's kind of figure out how these go. So the seek time is the time it takes to position the head at the track. So if when we start reading, you know, we're here and we were supposed to go to this track specifically, then the time it takes for us to actually move this, ignoring of the actual spinning, the time it takes for us to move the head in or out like that, so actually probably does better. So the time it takes to do this part, the horizontal movement there. Again, I'm moving the disc here, but what's actually moving is the head, okay? It's just that it's a lot easier for me to do this like this, because then I can spin it, okay? So the time it takes for the head to move here or here, and again, tracks are just the circles, that is going to be your seek time, okay? Then, the time it takes for the spinning to line up to the right sector within the track, so the time it takes for us to spin to where we want to be, so like, let's say we're here, and we're trying to go to the purple or the pink to the bottom right here. So the time it takes us for, first of all, seek time is going to be to move to this track and then to wait. The waiting time for us to actually spin the track, or at least wait for this to line up there, that is going to be your lag, your latency time, okay? So that's rotational latency. That's the time it takes. We got to wait for the spinning to line up to the right sector. So the moving of the head to the right track, that's going to be your seek time. And then us waiting for the disc to spin to the right spot is going to be the rotational latency. And finally, the transfer time is how long it takes for us to actually read the stuff or write to it as well. Which again, is going to be limited. I mean, imagine this. We could have a reading head which could transmit cleanly so much information per second. But if your disk is only spinning at like 5 revolutions per second, then you know, or actually, so let's say it's 5 revolutions per hour, like that, like super, super slow. Okay, it's like literally going like this. In that case, you could have this amazing head that could like read and write super fast. But if your disk is not spinning fast enough and it's always spinning at that speed, that's bad, right? So you kind of want to balance those out. But even so, there's going to take time for us to spin. Well, how fast? They ran about 45 revolutions per minute, or per second, sorry. No, per minute. No, that doesn't make sense. Yeah, 45 per minute. That does make sense. 45 and 70 revolutions per minute. I think that's how the disc players, how fast they spun. So yes, I'm not that old to know that. So yeah, my dad actually has his voice recorded in one of those when he was a kid, which is kind of cool. Okay, so moving on. That's the formula to do that. And again, how do you compute that? You can do it experimentally, I suppose, but you could also do the little math that I did above to figure out how long it takes based on the spinning and whatnot. The other formula that is useful to know, I suppose, is transfer time can be in bytes divided by number of bytes divided by rotational speed. So I'll put this one down. And again, the TA will probably do an example on Friday with these, so you can kind of get a feel for them. But these are definitely easier. Again, this actually makes sense why this is like this. Is B is the number of bytes to be transferred. N is the number of bytes on a track. And then C is going to be, or not C, it's just an R, sorry. Is the rotational speed, so the RPM, or RPS, I suppose. So revolutions per second. I suppose I never said that today, but I'm sure you all know what RPM stands. That one's revolutions per minute. This one's RPS, is revolutions per second. So yes, and I think most hard drives are two speeds. Again, it's like 5,000 and 7,000. But here, let me see it. Okay, here we go. So the standard ones are, the ones that I know is 5,400 RPM. So that's 5,400 revolutions per minute. And then the faster ones is the 7,200 revolutions per minute. Those are the ones that I usually see are sold. Like when you go buy a hard drive on Amazon or something, those are the speeds that you see. Not to support Amazon. But yeah, but there are some hard drives that can vary that up to about 10,000, which can be like specialized ones. But again, most of the ones you typically will buy are either 5,400 or 7,200. Okay, so that's kind of just something they came up with. And again, the faster ones are good because that means that the rotational latency is going to be less, right? That's going to be the big advantage. And that, so maybe the TA can do an example of how long it would take to actually compute this time in seconds, picoseconds probably, or however long it is, to spin the disk to the right spot. And the faster the RPM, the better. However, the faster the RPM, you need a better reading head to be able to keep up with the reading or writing to the disk as well. Okay. Oh, I guess it did have somewhat of a picture on the book. That kind of helped a little bit. Which was this one. They have the different labels as well. The spindle is just a stick where the thing is spinning. You know, it's stuck to a motor that actually allows it to spin constantly. Oh, by the way, technically there's an additional delay factor included, and that is the startup time. So like if your hard drive is stopped, it actually needs to spin up to the right speed, and then you can read from it, right? So I suppose if you're in a data center where the hard drives are not constantly on spinning, and you need to access something from a hard drive that's actually off, then the time it takes to speed up, like to actually get to speed, will be an additional factor to compute as well. But again, in most home computers, your hard drives are constantly spinning from the moment you turn the computer on to the moment pretty much the last thing you do when you turn your computer off. So as a summary, the physical characteristics, we have a fixed head or removable head. In the case of a fixed head, that's not very commonly seen because it's a lot of circuitry and unnecessarily. But the advantage of that is that there's no seek time, because if you have a fixed reading head on each track, then the thing doesn't need to move around, and so you're only really waiting for the rotational delay, right? And you can actually cut the rotational delay in half if you had read heads on this side and then on this side, and the thing is spinning, then you basically cut it so the slowest possible scenario is where it's right before, right? In a normal, actually, this is something good to talk about. In a normal hard drive, the worst case scenario is you gotta move the track, you gotta move the head from like the outermost track to the innermost track, for example. So that would be like the worst case scenario for that movement. And also, once you finally get to whatever track you're going, you just missed by one sector what you were out to read. So you gotta wait for basically an entire cycle around to get to it, right? That's the worst case scenario. Now, what is more realistic is going to be your typical average. So about half the time. So typically on average, you need to wait for about half a spin before you get to the data, right? And I guess I never finished talking about it, but why defragmentation of a hard drive was kind of useful was because ideally we want to take advantage of the principles of locality, right? And one of them was spatial locality, which means that information that has been used recently, can be used again. That's temporal. And then spatial is information that is after or before is going to be probably used in the future, right? And so ideally, with something like a hard drive, the way you can take advantage of that is if you are keeping, let's say you're watching a movie, you want to keep all of the movie in the nearby sectors, right? Ideally, you want to keep the movie flowing. Like in the first sector, you have the first second of the movie, then in the second sector, you have the second, and so on. Because then you're just kind of spinning it and reading it as you go. The other scenario is if there is, if your hard drive is almost full, it's just filling it wherever there's space is available, right? The problem of doing that is that it has to be moving a lot to find out the different places in the movie. So what defragmenting used to do back in the day is you would reorganize a hard drive so everything was basically next to each other. And that way there was less of the latency time and also the seek time. And you would kind of speed up the hard drive quite considerably, actually, when you would defragment if it was really, really fragmented. But defragmenting a hard drive would take a long time, as the hard drive is basically moving things around, especially if the hard drive was almost full, because I have to play Legos trying to fit things back and forth. So yeah, that's now finally the head mechanism. There's sort of three ways of doing it, which are there, and let me just actually draw them out for you. So in the easiest method, think of again like an old disk player, is the head is physically touching the hard drive. There's physical contact there with the magnetic tape, but it's a very light field. By the way, that's also important. You want to make sure this thing is super smooth, because if it has a bump in it, the whole thing will break down. That's why if you drop the hard drive and it got unaligned from this, even like by a millimeter, if this thing is supposed to be contacting, now it's like slobbering all over the place and the whole thing breaks down and you lose your data. Actually, well, you technically don't lose your data because you could probably replace the head and still recover the data, but you'd be paying quite a bit of money. So that's one of the simplest ways, and that's how floppy drives used to work. And it works okay, but friction is never a good thing, right? So that kind of causes some problems. So most hard drives for a long time had a fixed gap. So they had a really, really tiny gap, and I'm talking really tiny, like maybe 1 millimeter or less. And that was okay because the magnetic field was strong enough to basically go through that gap of air. Okay, and so that was perfectly fine. And that's how a long time it was used. That's known as your fixed gap. Okay. However, nowadays they created what's known as the Winchester aerodynamic gap. And that's how most modern hard drives are done nowadays. And that's actually kind of cool. It's like a little plane. And do you guys, well, I don't know if you guys know. Do you guys know how the aerodynamic of a wings work? Really small sideways here. That's not a good one. Okay. So a wing of a plane, the way you generate lift is you have pressure from the air coming in this way, right? And so when air hits the wing, it has to kind of go around the wing's shape, right? This is a longer distance on the top than the bottom, right? However, the air wants to kind of come back, the air particles per se, they want to kind of re-meet back here at the same time, right? They want to come back here at the same time. So like if two particles were together here when they started, they want to rejoin at the same time. but because on the top there's a longer distance than the bottom, these particles go faster than the ones in the bottom. And because they go faster, they generate a low pressure, and that generates lift. Okay? So what we end up doing in the third method here for the Winchester gap is the little head itself is a tiny aerodynamic wing. And that wing is normally actually touching the disc in the beginning. It's like a runway. And it starts spinning up. As air starts hitting it, it actually generates lift. And it actually floats above. It's like flying over the disc itself. Now, this might generate a little bit of vibration probably, but it's okay. It's a pretty enclosed air system. And so it actually is flying over the disc. And when your disc is turning off, it actually lands back in the disc. And typically, there's a special area for it to take off and land per se, so that it doesn't just stop and crush the data or do damage to the data. But yeah, so it speeds up, it takes off, and then as it moves back and forth, it reads the data, and then eventually it lands. And that allows the gap to be a lot smaller and to be able to read things better. So it's a really cool system, actually. Like, you got like aerodynamics in your computer, so yeah. So yep, that's how planes fly, in case you were not aware of that. I'm actually cool they talk about SIP cartridges in the book, because I had one of those, and like that technology died, and I was like, okay. I think we had like 2 of them maybe. They're like big fat floppies. They look like Nintendo 64 like games, but those were examples of removable hard drives per se. Floppies not really, because they're tiny, but the SIP cartridges were pretty big. They're like, I frankly thought they were the predecessors of flash memory, but then I realized they're actually hard drives, like disks. So yeah, okay. They talk about, here's the Winchester stuff. There's some statistics you can read on your own. Cache could be useful in your disk because you can, especially for writing, you can just kind of hold the information there and then write it later on. And also you can pre-cache. You can use prediction to prepare and read in some sectors ahead of time into a little cache locally in the hard drive that you predict will be accessed in the future, and you can help out to avoid the really long times that can be. It can take like 1 millisecond to actually read in your hard drive or less. So yeah. So anyways, that's pretty much all there's to it about like hard drives themselves. Before I talk about RAID, let me go ahead and finish talking about like actual hard drive. So let's talk about solid state drives first, and then we'll come back to RAID. That way we'll finish the lecture on RAID. So let's talk about SSDs. SSDs are like one of the greatest advancements, I think, in terms of computer speed in the recent years. Although I think nowadays they've been around for a while actually. SSD stands for solid state drives versus HDD, which stands for hard disk drives. And SSDs are faster in read and write time. They last longer in terms of if you're not using it, they last longer because one of the things that can happen with an old hard drive is because it's actually spinning, and spinning wears things down because it's a motor, and motors wear down over time. It's just a fact of life. With a solid state drive, there's no spinning involved, and so they technically are supposed to last longer if you don't use them. Okay, now there's a big if there because they're new technology as well, so obviously we haven't left one for long enough to see if it degrades or not. We actually haven't even left hard drives long enough to see if they really degrade or not. So it's kind of arguable about that. But in theory, they should last longer because there's no mechanical part. However, hard drives do have less write and read capabilities in the sense that you can only write to a solid state drive maybe like, the book says it, but it's something like 100,000 times per sector or something. And so what happens is, the memory degrades after time, and it doesn't allow you to read and write to it. And so this can be quite a bit of a problem actually, because whereas a hard drive, you could read and write as long as you want, it's probably going to fail mechanically before it ever fails in terms of being able to read and write to a sector. The SSD, in theory, should only last about 7 years of regular usage before it starts to really degrade and lose information. But yet again, we really haven't had them that long to truly see this. However, there is some technology like TRIM that the book mentions called TRIM, and then another one which basically distributes evenly the read and write operations. Also, because this is using kind of RAM in the sense of random access memory, the ability to write and read from anywhere. It also one of the things, if you look back at how flash memory works, flash memory writes in blocks, and main memory works in terms of pages, which I'll talk about in the OS in 370, but CS 370. But basically, you can only write into this big blocks in the SSD. You have to erase the whole block and then write into another one, right? So if you have a really tiny file, you have to erase the whole block, and that wears out the block itself. So you're not just wearing out the tiny piece that you're writing, but the entire block. And so what the computer tries to do to even out the erosion of disk, or well, not disk anymore since it's solid state, but the erosion of the drive, is that it either has like a caching system, or it just tries to keep track of what sectors have been written to the most, to write less to those and write to ones that are not. Also, if a sector is not really being used at all, then it just can clean it up ahead of time and use that one. So it's not trying to like basically write to the same spot too many times, because that wears it out prematurely. And so that's basically what they talk about in terms of practical issues here. Yeah, it's basically the last chapter, the last paragraph of that section. As flash also stressed, they lose the ability to record and retain value. Typical limit is 100,000 writes. Techniques for prolonging it include fronting the flash drive with a cache. Yeah, what I said. And then an algorithm that evenly distributes the right access blocks of cells, which I think is called trim. I could have sworn I even saw the word trim being used in there somewhere. But, oh, here we go. Another technique is the trim command, which allows operating system to inform the SSD which blocks of data are no longer considered in use and can be wiped. So yeah, you can go ahead and read that. If you save your SSD space by only saving important things to it, does it delay the degradation? Basically, the less writes you do to the thing, reading you can read as much as you want. It's all good on that. Writing is what wears it out. The less writing that you do, the longer it lasts. However, I would say just not worry about that. Reason why is this: Moore's law, kind of in a way. Hard drive prices are going down, or at least staying the same, but the space is going, the cost per bit is going down, because right now what you're paying for a 1 terabyte SSD is the same price that you would have paid for like 128 gigabyte SSD like maybe 4 years ago. And so you got this 1 terabyte SSD you love and you want a baby. But the thing is this: 7 years from now, when like in regular usage terms your SSD would be nearing its end of life, and there is, even as the book says, there's software that will warn you about that. By then, as equivalent size SSD will not even exist. Like, they will be gone. There's going to be something that is way, way bigger for the same price or cheaper. So there's no point in trying to baby this thing when it's going to be worthless by the time that it would have died anyways. So just use it all you want. Don't abuse it, obviously, but use it all you want. And then in 7 years from now, when you got to upgrade, you can buy the cheapest SSD back then, and it's going to be way, way more space than the one you have now. So that's kind of the thing. That's true. I built my PC 6 years ago. I saw the SSD were super expensive because I bought one back then. Yeah, they're extremely cheap now. Especially if you go on like Black Friday or something, you can get an SSD for like super, super cheap. So I'd say, buy once, cry once, and then use it as much as you want. Obviously, be smart about it. Don't try to record live streamings into it. Or things like that. Use a hard drive for that. But for normal uses, I say use it fine. Video games, things like that. The advantage is, the amount of time you would lose in your life by waiting for things to load, and that the amount of time you save is worth it, frankly. But anyways, back to this. Another pro of that is that they're quieter. There's no spinning, so that's always a nice thing. If you got a computer, you still probably have the cooling that actually makes noise. But this is one less thing that makes noise, okay? Tablets don't make any noise at all because they're all solid. There's no hard drive in it, and there's no active cooling in it, actually. Well, active cooling is a finicky term nowadays. But basically, there's no moving parts, and that's also one of the ways we achieve that is because we have something like an SSD. And now we can talk about NAND, right? Actually, so SSDs use NAND, but I never really talked about NAND and NOR, okay? So there's NAND and NOR are the two sort of main types of memory. The NOR works in the basic unit of a bit, And then the NAND is, the basic unit is like 16 or 32 bits, so it's a bigger sort of block per se. They're both great, but they have a little bit of pros and cons. NAND does not provide technically random access external address bus, so the data has to be read in terms of blocks. So don't get this wrong, NAND is still RAM, but what I'm saying is NAND is RAM in block pieces, not in individual bit pieces. And that's why you got to erase an entire block when you're working with this thing. Whereas NOR allows you to have addressing to each individual bit, but it's more expensive. And it typically used, NOR is typically used in things like BIOS and OS system code because you want it to be fast and tiny and it's okay. NAND is what you typically use in solid state drives, flash drives, memory cards, and so on. And again, the only disadvantage of NAND over NOR is that NAND is dealt in blocks, and you gotta erase a full block or write to a full block. But again, those blocks are pretty small, 32 bits, 16 bits, or even if they're bigger, they're still small in relative size. But that is also one of the things we gotta consider for wear. So yes, thanks Moore, and thanks Moore's Law. So yeah, okay. Practical issues of that we already talked about. CD-ROMs. Let's talk about CD-ROMs. I don't even know if we're going to get to read today. We'll have to talk about it tomorrow. We'll see. But CD drives. So CD drives. Here is what a CD drive looks like. Well, this is DVD drive technically, right? And again, what isn't here is a laser, and they probably should tell you somewhere. Attention, class 1M visible and invisible laser radiation when opened. So this one I just saw, so I took it out. Basically, CD drives are really, really cool technological advancement because the amount of information you could store in such a small amount of space was quite an accomplishment at that point in time. You could store about 700 megabytes in a disk, in a CD drive. CD stands for compact disc, and there was different kinds. There's CD-ROM, where CD-ROM is read-only memory, and those are the ones that usually you get stamped. So here they talk about it. Yeah, so it's a polycarbonate resin, and you make a master disc, and that's why there's an award for musicians that's called like a disc of gold or something. I don't know what it's called. Maybe you guys know in chat. And it basically what they do is they make a little mold, because the way that the disc is made is, again, there's little hills, pits, and dips in the disc. And so unlike a hard drive where it's magnetic, here it's optical. So the pits you could think of as highly reflective material, like a mirror, and the hills you can think of as like non-reflective material, so like dull stuff. Okay. And basically, if it's shiny, you hit a laser and it shines back, that's your one. And if it doesn't shine back to you with the same intensity because it's like a dull material, and by dull I mean like non-reflective, then it's a 0. Okay? So what you do is you can, depending on the way that you stamp it, you can make it shiny or not shiny. And so the master disc, I forgot what they're called. What are they called? Well, they call it here master, but I'm thinking what they're calling in the music industry. But they award them to musicians when they sell a lot of discs. But anyway, basically the master disc is a big stamp, and they just stamp these polycarbonate disc, and bam, you have your disc fully functional. And that's a very cheap process to do once you have a master. Making the master is expensive, but once you have it, it's just like stamping paper. You're stamping. You're making all of these discs out of that. They're read-only because you can't mess with it once it's done, right? And you cover all of this usually with some sort of coating to avoid scratches and things like that. That's why back in the day, when you had a scratch in it and it wasn't reading it, you would buff it out. And the problem it wasn't reading it is because it couldn't get through the cover, because the cover is usually just transparent, so you can see the pits and the hills, right? But if it's fuzzy, if the cover's fuzzy, then they can't see them. The laser can't see them. So you would buff it out and clean it and make it transparent again so it could read through. So that was a thing you would do back then. I mean, I'm sure you still do it nowadays, but nowadays they're far more resistant, like Blu-rays and things like that. So here's an example of that. As you can see, here's they're called lands, I guess, the hills. The lands and the pits. And so depending on the land and the pit is whether it's reflective or not as well. No, not vinyl records. It's something else. What do they call them? Master CD Record Award or something. I don't know. CD sell. Let's see. Like when they say platinum records and things like that, and they give them the little discs. It's like they give them the gold disc that they used to stamp it with. I don't know. It's okay. It's unrelated. I'll find it and then maybe I'll post it as a comment on the YouTube video once it gets uploaded. Yeah, I'll probably do that if I remember that. So if you're watching on YouTube, click down to see what I'm talking about. And if it's there, I remember it. If it's not, then we will never know. So yep, golden record, maybe golden record. Yeah, maybe that's what it might be. If it's a golden record, because they could use it as a master to be the golden record. I don't know. Maybe I'm crazy. Is Blu-ray the same technique? Yeah. So let's talk about higher density. Basically, same thing as a hard drive. The smaller that you can make these lands and pits, but still be able to read them, the more information you can store. However, you need to make the laser smaller. And how do you make a laser smaller? You increase the frequency of it, which changes the color. And while these lasers, I believe, were reddish per se, the ones on Blu-rays are bluer because of the higher frequency. Because if you look at a chart, red is on the low end, and then like purple or blue is on the high end. Well, I guess you're looking this way with this way. And so because of that, so this is red and this is blue. Because of that, we call them Blu-rays because it's more of a bluer laser per se. Okay, so that's why they call them that. But yes, you're right. It is just the same technique, just more efficient. And the protective acrylic on the top is what protects you from not messing with this. Again, that's the one you buff out if there's scratches so that it can read through it as well. So there's different. There's a chart hopefully somewhere here of the different CDs. Well, there's this one here. There's CDR and CDRW. Just R means recordable and RW means rewritable. Recordable are ones that, and where you would buy the discs and you would only be able to write to it once. And then RW were ones you could rewrite multiple times. The way they actually work with the R disc is you would shoot a sort of a medium power laser that that actually would modify the disc by, so it all, think about it this way, it'll all start super shiny. But the parts that you hit with the laser, you would make less shiny. Which you can think of this, all of this starting out as everything set to 1. And then the parts you want to make 0, which are not shiny, you would shoot the laser, which would kind of like, quote unquote, again, this is a little bit of exaggeration, but it would melt the actual material, the polycarbonate or whatever, to make it less shiny. And now you were able to write into it per se. You know, you only have to write the zeros in. The ones were already written. That's just an example. That's kind of how it would work for the most part. The RW ones, the rewritable ones, they work with a different system where they have a special material that has two phases. Depending on how you shoot a laser to it, it changes the phase of it from a crystalline effect to a not crystalline effect, I suppose. So basically, you shoot the laser to this particle, it becomes shiny. And if you shoot a laser in a different way to the particle, it becomes not shiny. It's just that's chemistry. Don't ask me exactly how that actually really works, but you just do it that way. And then doing that, changing the phase back and forth, allows you to basically set it to 0 or 1. However, eventually it wears out and it doesn't change that easily. It requires more energy to the point where it's impossible to do, at which point you discard it. But that takes a lot of read and writes to it. You'd be surprised that CDs are actually quite reliable and should last us for over 100 years or more. So that even rewritable ones too. It's only the writing and reading activity that actually wears it out. But once those particles are set to a certain state, I'm sure they will outlive us all. So that's pretty much the difference between CDR and CDRW. Then we have dual layered CDs, dual layered DVDs. Actually, dual layered CDs, I don't know. No, they did have dual layered CDs, I think. But DVDs, they definitely had dual layered DVDs, which were like the commercial movies came in those. And nowadays they have dual layered Blu-rays. And the way they work is they basically stack them both, but there's still only one reading head. And the way that you can access the second layer is by changing the focus of the lens of the laser. The lens in the laser, you change the focus of it to be able to read the layer underneath. So you basically have them at different focuses. And that's some optical magic that is beyond the scope of the course. I bet you not even the CP people know how that works. But who knows? So yeah. Why can I think I crashed. Oh, there we go. It's back. It's lagging. Okay. I wish I could. It's not letting me switch to that one. Oh, now it's going crazy. It's just a big delay when I click on the button and it switches the picture. I wanted to see that picture because it might be useful. So here's an example of the different sizes of the laser. And here's a CD, a DVD, and a Blu-ray, as you were saying. It's the same thing, just smaller. The smaller the laser's width, basically, the smaller that it can scan without getting confused with the other ones around it, right? And so higher frequency laser means that it's a smaller wavelength. And so that basically allows you to read a smaller piece. So in theory, whatever comes with the Blu-ray someday is just going to be a laser of a higher frequency, which is probably more dangerous technically for us. Like, it might make us go blind, I think. In fact, even Blu-rays could make you go blind. But again, it's all inside the machine, so we're not worried. So it's basically able to shine the light and see if it's shiny or if it's not shiny, and that's how you know if it's a 0 or a 1. Okay, so that's Blu-rays for you. Finally, magnetic tapes, and I guess we'll cover RAID next time. Magnetic tapes are old school, but as I was informed, I think yesterday or at some point this last week. By one of the guys that works, one of your people, one of the students that works at the IT and CS, is that we actually do still have magnetic tapes at the UNLVCS department to store data, and that is because there's a lot of places in the world that still use magnetic tapes, and the reason for that is because it's very cheap. There's a lot of it. It was produced and it's just there, so might as well still use it. Magnetic tape is another way to store data. And the way you typically store data there is in little tracks that are horizontal to the tape and sort of serpentine. So they kind of, if I draw it for you really fast. You got your tape, so you got our tapes, and then you got the tape that's going around. And if we flatten out the tape and look at it like a top view, then it's sort of serpentined around. So here's a track of the tape that goes all the way to the end of the tape. And then it goes back this way, and there's another track, and then it goes back like that. So it basically has this shape to it. So if you're reading it, you spin it all the way to one end, so you read the first track, and then you spin it all the way back to read to the second track, and so on. Or you could have multiple read heads read in parallel, or you could just move the read head back and forth between different tracks. So you could see the tape moving back and forth in multiple directions. The reason why they don't put everything like this, so like in this shape, is for efficiency of reading and writing. It's a little bit better to put it in this format because you can just jump quicker between the data. You still try to take advantage of locality of reference, especially spatial locality. But if you're reading something here and here, that's the worst case scenario. So you're kind of screwed there. But yeah, basically that's made of polyester, like clothing. But then they put magnetizable material on top, and then they magnetize it. So it's the same still idea of just magnetizing stuff. Again, that's no new. That's old technology that was just been implemented to other things. But that's pretty much how it works, and that's all there's to it. Other than that, not really much point in talking about that kind of technology because it's kind of on the way out. Is magnetic tape durable? Yes, it is. I do believe that it can. Okay, so like VHSs, which are magnetic tape, will degrade after like 30 years. So you could have data loss, but at least in terms of not time, but in terms of actually like you could take a beating, it can take a beating. It really depends on the material. So some like magnetic tape that's used in like hard drives and stuff is pretty durable. VHS specifically in those kind of special cases are not that durable. So yeah. So that's it. I guess we'll talk about RAID next time. The different RAID systems. That's okay, I guess. I was hoping we'd cover that today, but it's okay. So either way, start looking. Chapter 8, I'm just going to go do a really quick crash course on and brief it. I was going to actually skip it, but I'm going to go really fast on it. So I'll do that tomorrow, and then we might skip chapter 9. So keep track of Discord and the Canvas. By the way, I did put up a poll if you want me to have the live lectures or if you want me to have pre-recorded lectures. So go ahead and vote on that. But yeah, that's pretty much it. So hope you guys respect hard drives now, I suppose. If that means anything. If lectures were pre-recorded, how would you handle participation? Participation would be strictly focuses on the Friday lectures. So the discussion, because the discussion sessions will still be on live with the TA. So the rest of the participation points would come from that. And there's only one of those left now, I think. Unless we do one on the last week. But we have the test to do as well, so yeah. So yeah, make sure you vote on that. I'll check the votes later and figure that out. All right then. Well, have a good day. I'll see you guys tomorrow. Bye.